Hi, it's Jonathan from The Gift of Maths. Today, I'll be talking about the mathematical law in chemistry that governs the spread of disease in rabbits and foxes. So here I've listed the prerequisites for this video. Just knowledge from a first course in calculus will be sufficient. In particular, you should know that the derivative with respect to time, that represents the rate of change with respect to time. In addition, some basic chemistry knowledge that would be helpful as well. Alright, so I first have to tell you what law I'm talking about, and this is the law known as the law of mass action. So the law of mass action states that the rate of a chemical reaction is proportional to the product of the amount of each reagent, i.e. the chemical particles that are reacting together. So we take a standard chemical reaction, so that's A plus B gives some combined thing, AB. Then the law of mass action tells you that the rate of reaction is proportional to the amount of A multiplied by the amount of B. The rate of reaction, that's the rate that AB is being produced. So that's given by the derivative with respect to time of the amount of AB. Therefore, the AB dt equals Ka times B. So K is just the constant of proportionality, and the square brackets here is just the standard way in chemistry to denote the concentration. That's equivalent to the amount. So what we have now is that the rate of increase of the concentration of AB is equal to K times the concentration of A times the concentration of B. Let's now look at a different type of chemical reaction so we can see the law of mass action in effect again. So now we're going to look at a particle AB that splits up into individual particles A and B. The law of mass action tells us that the rate of this reaction is proportional to the amount of AB. So the rate of reaction, that's just the rate of increase of the concentration of A and also the concentration of B. So we get dA dt, that's the same as dB dt, and that's equal to K prime times AB. Here, K prime is just the constant of proportionality. And like before, the square brackets just denotes the concentrations. So where would you use this in chemistry? Well, in chemistry you know about reversible reactions, that is reactions that can go in one direction and also in the opposite direction. For these type of reactions, the reaction going in one direction balances out with the reaction going in the opposite direction, reaching what is called equilibrium. So in other words, at equilibrium, the rate of reaction going in one direction is equal to the rate of reaction going in the opposite direction. So by equating the rates we had previously, we get the following, and then just rearranging this, we get K over K prime is the concentration of AB divided by the concentration of A multiplied by the concentration of B. Now, the term on the left is just a constant, so we can combine it into one, and this constant is called the equilibrium constant. So I'm not really a chemistry expert, so any experts in chemistry out there, if I've made a mistake or you have any comments, feel free to leave it in the comments below. We now look at modeling the spread of diseases, and you'll see how the law of mass action plays a role there, despite being a law from chemistry. The most basic model for modeling the spread of diseases is the SIR model. In the SIR model, the population is split into three groups, S, I, and R. S is the susceptible population, I is the infected population, and R is what is known as the recovered or removed population. So I'll say a little bit about each population. S, the susceptible population, represents those who might get the disease. I, the infected population, represents those who have the disease right at this moment. And R consists of those who recover from the disease or those who actually die from the disease. Now, it's a little strange that we lump these two groups together. The idea is that we don't consider them as having a role to play further in the spread of the disease. So these three populations form the SIR model. As time progresses, as the disease spreads, the number of people in each population will fluctuate, and this allows us to understand how the disease is spreading through the population. So first, a word about mathematical modeling. Whenever we use math to model a real-life situation, we have to make assumptions. Now, the relevant assumption in this video is that the populations are mixed. What this means is that individuals in the entire population have an equal chance of meeting each other. So how is that relevant in our situation? Well, it means that we can model encounters between each individual as if they were particles in a chemical reaction. And this is why we can apply the law of mass action. So let's now consider how people in the susceptible population get infected. Now, to get infected, a person in S has to encounter an individual in I. In other words, someone who has the disease. So the law of mass action tells us that the rate of people getting infected is proportional to the number of people in S, the susceptible population, times the number of people in I, the infected population. Now that means that the rate of infection we can write as beta over n times S times I. Beta over n here is a constant. In particular, n is just the total population. So now we consider how people in the infected population move into the recovered/removed population. Now you can only enter the recover/remove population if you are infected, and it doesn't depend on any other population. So the law of mass action tells you that the recovery rate is proportional to the number of infected individuals. Hence the recovery or removal rate is equal to gamma times I, where gamma is a constant. So these two facts alone allow us to determine the system of differential equations that constitute the SIR model. So we'll first look at di dt, that's the rate of change of the number of people infected. Now there are two parts in this. The first part is the people that get infected, that come in from the susceptible population. From what we had previously, that's given by beta over n times S times I. So this represents the infection rate. We next consider the people in I that either recover or die. That's given by minus gamma I. So this is the recovery/removal rate. So now we consider the rate of change of the susceptible population and the recovered/removed population. Since the population S is decreasing as people get infected, we have ds dt must be minus beta over n S times I. Similarly, R is increasing as infected people enter the removed population. And so, dr dt is equal to gamma I. So there you have it. This is the derivation of the SIR system of differential equations. The solution to this system of differential equations gives rise to the familiar graphs of the S, I, and R population numbers that you often see in news reports. And the entire model can be derived from a simple mathematical law in chemistry, the law of mass action. We now look at a predator-prey model. This models the number of a predator and the number of a prey in some population. So we let X be the number of prey, for example rabbits, and we let Y be the number of a predator in the population, for example foxes. So here, I'm going to take a different approach from before. I'm going to give you the system of differential equations, and we'll try and understand it through the lens of the law of mass action. So this is the predator-prey model due to mathematicians Lotka and Volterra. This is the following system of differential equations. dx dt equals alpha x minus beta xy, dy dt equals gamma xy minus delta y. Alpha, beta, gamma, and delta, they're constants. We have to make the same modeling assumption we did for the SIR model. In other words, the population of predator and prey are mixed. Each predator and prey have an equal chance of meeting each other. So the law of mass action applies. So looking at this system of differential equations, the law of mass action tells us that the beta xy term and the gamma xy term are due to encounters between predator and prey. The term in dx dt is negative because when predators encounter prey, when foxes encounter rabbits, they eat them. And the term in dy dt is positive because eating rabbits increases the population of foxes, they get more food, and so on. The remaining terms alpha x in dx dt and delta y in dy dt, they're due to the natural change in population of the prey and the predator in the absence of the predator in dx dt, and in the absence of the prey in dy dt. So this is the Lotka-Volterra system of differential equations. The solution to the system of differential equations gives the following graph, and you can see they make sense. As the level of predator rises, the level of prey goes down, and vice versa. So in this video, you've seen how important the law of mass action is. Even though it comes from chemistry, we've seen how important it is in different fields, and this highlights the interdisciplinary nature of scientific research these days. So thank you for watching this video. I really enjoyed making it. I think I'm gradually getting the hang of making videos for YouTube. If you like this video, please subscribe, and I'll have more videos in the future. In the description below, I'll have some further directions that you can consider if you're interested. Otherwise, thank you for watching this video. Have a good day.